So in a kind of analog to Lost Stars, there's been on the attendee mailing list some talk about morning running, or I guess running anytime. I can attest that it's very beautiful outside and a great place to run. So hopefully there'll be more. I didn't actually pony up. I did go running today, but I didn't say that I would, so I don't know if people did it and they didn't, and they organized separately. But I'd say, let's try and keep the outdoor activity going, and they won't be penalized or lost stars if you don't end up doing it. But if people are game for that, there's also great bike riding with those kind of rental bikes stationed right nearby where you can rent for an hour or two and drop it off somewhere else. And anyway, next talk is Peter Laprakov talking about unbreaking things, which I think everyone here would like to unbreak something.
Thank you. Good morning, everyone. I'm Peter, network engineer at Facebook, and the topic of my talk is debugging large-scale networks. Before I start, I'd like to thank those people who made this talk possible. Their hard work, coding, and operations drove the system for the past 2 years. We first started by looking at the process that people commonly use to debug the network issues in their networks. But first, let's take a look at Facebook's network architecture. First one is data center. Our data center is based on a closed topology, multiple stages. As you can imagine, it has lots of links and devices, but otherwise, it's a very well-known and common topology. Our specifics is the fact that we use BGP for routing, only BGP, nothing else, and that majority of our traffic, over 95%, is IPv6. The things that make this network hard to debug is very large equal cost multipath fan-out. At some cases, the fan-out is as large as 120 devices. We also have a mix of layer 2 and layer 3 ECMP together, which makes things even harder to isolate. The backbone network. The backbone has much less devices than data center, but runs much more protocols. At the heart, there's the MPLS core, which runs on the backbone devices. These guys run the ISIS, RSVP, all these protocols you typically expect in the backbone, and they use the outer bandwidth to do traffic engineering. At the edge of a network, there are data center routers. These guys serve as the IP to MPLS edge, and they connect the data centers to our backbone. The two major challenges that make this network hard to debug is the outer bandwidth, which keeps changing the paths that the LSPs take in the core. And second one, the fact that we have to use the equal cost multipath at the edge of a network when we place the traffic on the LSPs. All right, so how do you commonly debug these problems? Well, usually we use SNMP to pull the counters of the boxes. Counters like packet drops, interface rates, all those usual things. In cases when you can't pull something over SNMP, we have to use screen scraping and pull the unknown counters, say internal fabric drops from the network devices. There's two major problems with this approach. First of all, SNMP and CLI scraping is slow. At the very best, we can get the data at the periods of 30 seconds. And secondly, it's not reliable. We used to have lots of issues that don't show up in the counters, nor SNMP, nor CLI. In cases like this, the human being has to resort to an end-to-end debugging. We have to run the on-host tools, HPing or NPing, which allow us to simulate the application traffic. For example, HPing allows you to inject TCP packets. We have to run these guys with the varying source ports. This way, you can explore the multiple paths in the network and overcome the problems with the ECMP. And lastly, once you see the broken path, you can run a trace route and isolate the fault point. And the key conclusion from this is that ping and trace route are still very important tools in network debugging. So let's see how these principles generalize to a larger scale. In this section, we're going to talk about NetNORAD, the system for automatic end-to-end fault detection. At its very heart, the idea is very simple. We have all the servers at Facebook, and we make some of these machines run the pinger processes. Every machine at Facebook also runs the special responder process, and these guys work together by sending the probe packets across the network and collecting the loss and round-trip time. Once I have this data, well, then we run some sort of analysis to extract and try to find the faulty locations. Now, a few words on system evolution. It all began slightly over 2 years ago, and first implementation was a very simple Python script which ran on the servers and invoked a ping command. The primary goal was to detect the round-trip time between data centers. The second version was slightly more advanced. It was actually written in C and using raw sockets to inject TCP packets. The idea here was to collect packet loss in the network, not just latencies. We hit some issues with this approach. Specifically, if you use TCP probing, you have to reset the server state to avoid the SYN flooding attack. What happened in this case is TCP resets were spooking the host monitoring systems, and we had to resort to using ICMP. So ICMP was pretty good, actually. It was very efficient. The kernel response, you can embed timestamps and all those things, but we hit some problems I'll explain later. The current implementation is UDP-based. In this approach, we have pinger and responder processes which use UDP to detect end-to-end packet loss. So let's review these guys. As you can expect, the pinger injects probes and responder replies them back. Both these guys embed timestamps in the probes, so we can measure the round-trip latency pretty efficiently. The pinger has to be very efficient. Since we have much less pingers than responders, we have to ping at a very high rate. In some cases, this goes up to 1 million packets per second. The responders, on the other hand, don't have to be as performant. All they have to do is simply reply back with a packet. We have multiple traffic classes in the backbone and data center, so we have to probe every class separately. That is, the pinger has to inject probes for every DHCP value. These guys have been open source today. We hope you find it useful. It's in C++, but I hope you folks like this language. I know, I got this a lot. OK. The very important aspect of the system is placement of pingers and responders. We have a special Python script which runs every 5 minutes and allocates machines to be used as pingers. At the very least, we have to pick up a cluster in each data center and allocate at least 10 racks in every cluster. Inside every cluster, inside every rack, we pick at least 2 machines for pinging. The idea here is to have a good striping so we don't have a single rack or a single machine affecting our probing. The targets are easier. For targets, we have to pick up at least 2 machines for every rack of servers at Facebook. To pick up targets, we have to consult the host monitoring system just to make sure we don't pick up machines with low memory or high CPU or some other issues. This allows us to reduce the amount of false positives. Timestamping is a very important part of NetNORAD. As I mentioned, we embed timestamps in the probes. We use kernel timestamping because in UDP you have the packets going from app to app, and kernel timestamps allow you to eliminate the delays caused by socket buffers. This data is not only used for measuring path stretch or congestions, but is also used to auto-tune the application timeouts. We collect the samples every 5 minutes and feed them into the system that tells our apps how soon they should time out when connection doesn't succeed. Very often, we're being asked why use UDP for probing. Indeed, majority of our traffic is TCP, probably 99.9%. However, as I mentioned, we hit this problem with TCP resets, causing the false positives to the error monitoring systems. And ICMP, as I explained further, had other issues. UDP, from a perspective of equal cost multipath, is being treated the same way as TCP. We use the source port and source-based IP addresses to load sharing in the networks for UDP. It's very good on the host side. It's receiver-side scaling friendly. You can very efficiently load balanced packets across multiple CPUs. And best of all, UDP allows you to have custom probe. You can add more fields and more data to a probe, and this allows for future extensibility. So this slide summarizes few issues we hit while deploying NetNorad. First one is the ICMP. As I mentioned, ICMP was great, but the major problem is polarization in presence of ECMP. Normally, all devices hash the ICMP packets using the source and dest IP addresses only. This means you can miss some paths and only probe a given host on a single path. Using UDP allows us to eliminate this problem. Secondly, and surprisingly, we hit some problems with IPv6 fib lookup on the hosts being slow. In the older kernel versions, the code that handles the IP lookups was pretty inefficient. So we had to move to a new kernel where our engineers have fixed this problem. And this change has actually been upstreamed. The high CPU boxes, which we have a lot, especially like in Hadoop clusters, used to cause lots of pain because the responder used to drop packets because of high load. However, a very simple fix in responder, specifically using multiple threads and pinning them to the RSS CPUs, practically removed this obstacle from production. Checksum offloading on some NICs proved to be painful. Since we use raw sockets for packet injection, some drivers and some NICs firmware were silently dropping these packets in transit. This caused us a few very painful hours of debugging, but in the end, we simply disabled the checksum offloading on machines that do pinging. Since we only have a few hundred machines that ping, it doesn't affect the general fleet performance. All right, so now that you see how we produce the probes, let's see how we process the data. There are a few major challenges here. The total aggregate traffic from pinging is on the scale of multiple hundreds of gigabits per second from all these pingers. We have tens of thousands of targets and hundreds of pingers. Together, this generates a very large volume of time series to analyze. The key insight to scale this was realizing we don't really care about a single host health. We mostly care about a cluster health. To better understand this, let's look at Facebook's network hierarchy. At the heart of a network is our backbone. The backbone connects together the regions. A region could be something like Primeval Oregon, where we have multiple physical data centers, and also connects the multiple points of presence, POPs, which we have all over the globe. In every region, we have multiple buildings or data centers. Inside each data center, you have clusters. Clusters group the racks of servers together. As you can see, the same structure repeats inside the POP. In this design, the cluster is the logical unit which we really care about. So first of all, I mentioned we don't really care about machine inside the cluster, but we still keep track of their health. This picture shows you the layout of a single cluster with 4 cluster switches and multiple rack switches. Inside each cluster, we run pinger processes on some machines, but we actually probe every machine in this cluster. What this gives us is time series of packet loss per machine and per rack. And it's a very large volume of data, and this gets stored into the H-based backend. This data isn't real time. It lags it by probably a few minutes, but we mostly use this for historical investigations. Now the heart of the system, building the time series about cluster health. So imagine you have a cluster of machines. It's probably tens of thousands of machines in one cluster. And for each cluster, we built 3 separate time series. The first time series comes from the data from pingers in the same data center. The second time series comes from pingers which probe our cluster within the same region, but different data center. And the third last time series comes from the pingers which are outside of the region of this cluster. So this gives us 3 different points of view on the given cluster's health. Same data center, same region, and from outside of a region. So this allows us to perform a very coarse form of fault isolation. For data which comes from outside of a region, we measure the packet loss end to end, and this includes the loss in the backbone and data centers. For data which we collect inside the same region, we measure the packet loss which only affects the devices in the same region. And lastly, for the probes which come from pingers in same data center, we try to detect the loss specifically in the cluster switches. Now that we have this time series, the question is how we process them. The heart of the system is Scribe. Scribe is a distributed logging system that allows multiple publishers and subscribers to exchange data in real time. A similar open source project is Kafka. Facebook used to have open source version of Scribe as well, but unfortunately the support has been abandoned. The pingers write data to this pipeline, and the data in this case is a packet loss time series. And the processors on the other side read the data from shards and process this in real time. The most important property is that it takes probably a few seconds to publish and consume data in Scribe. Worst case is 20 seconds, but on average we see the delays of 1-2 seconds. Real time here is very important for processing. Okay, so let's see how the processors build the time series. As I mentioned, the processors are the data consumers. They collect the packet loss samples from pingers, and for every cluster and for every proximity scope, we build a separate time series. It's very important for this time series, we don't track average, we only track multiple percentiles. For example, the 90th percentile allows you to eliminate the 10% outliers which have noisy data. For every time series, we define 2 thresholds, raising and falling. This allows you to alarm when the time series crosses the raising threshold and clear the alarm when the time series goes below the falling threshold. The combination of 2 thresholds allows to eliminate the whiplash behavior which comes from a single threshold only. With this design, we can detect packet loss event in less than 20 seconds average. This fact is very important because for operations, it's extremely important to be able to respond in real time. I think if you would actually delay the alarm by more than 30 seconds, it would be useless for our operations. The next stop for data is Scuba. Scuba is an in-memory storage that allows you to process time series, slice and dice, graph it in real time. But it's all interactive, done by human. The open source equivalent is InfluxDB. If you care to use it, it's actually pretty good. There's a paper on Scuba available online, but unfortunately, Scuba is not open sourced. However, we found out that visual analysis is an extremely important part of our experience, and Scuba allows our engineers to perform pretty sophisticated data analysis in real time. False positives is a bane of any monitoring system. In our case, we experienced a few specific cases, which are probably most important to review. First one is bad targets or bad machines. If you track packet loss for a cluster of machines, a single machine which reboots in this cluster would cause you a spike of packet drops and may cause you a false alarm for the whole cluster. This is why the pinger process implements the outlier filtering and eliminates the bad machines from the population before it submits it to the analysis. Slightly more complicated is a bad pinger problem. if you have a cluster which runs bigger machines, a failure in a cluster switch will make all these guys think that they see packet loss everywhere. And it's hard to remove this because the population of pingers is very small, and you can't really define a baseline of packet loss. To get rid of this, we need more data. For every cluster, we collect the packet loss into this cluster from the pingers in the same data center and same region. This allows us to identify the bad pinger clusters proactively and ignore their data. All this logic is done only at post-processing stage because a pinger is not aware about its surrounding. Quick summary about NetNORAD. So first of all, the pinger and responder asymmetry, that is having much less pingers than responders, was critical to scale data processing. Second one, being real time was probably the most useful property because otherwise system would be useless for our operations. We used the structure of our network to group the loss samples in 3 categories, which allowed us to perform some sort of fault isolation quickly. And lastly, we had to work, I would say, work a lot on removing false positives, because initially this used to be a very noisy system. Okay, so detection, just the first stage. By detection, we only know there's a problem, but we don't know where it belongs to. As I mentioned, by using the proximity scopes, we can already identify the fault location with some approximation. For example, if we have a cluster and the pingers in the same data center report no loss, while pingers in the same region and outside of a region report packet loss, we may conclude that the packets are being dropped at data center level, most likely in the spine switches. The next very helpful functionality is downstream suppression. If we have multiple clusters in same data center, all firing alarms, and we know they all belong to same data center, we can simply aggregate this alarm into a single folded big alarm for data center. This was very useful because otherwise, for a single issue, you'll probably see 10x more alarms than you actually need. So combined, these two together allow you to identify the approximate fault location. For example, you can figure out, oh, there is a packet loss probably in cluster switches in cluster X. Unfortunately, there's too many devices and links left to analyze. The next usual step is going over device counters, the same as SNMP and CLI stuff I mentioned, and trying to see if there's any obvious anomaly there. If this doesn't tell you, well, you have to resort to trace route. In our case, it's not usual trace route. It's the tool we call ABITO-SRT. ABITO-SRT is a special version of trace route built specifically to explore multiple paths in the network in parallel and identifying faults across these paths. On this diagram, you can see 2 machines which are being connected by closed networks and numbered devices, and with a single link which has packet drops. Our goal is to identify this packet loss. ABITO-SRT works by injecting packets with varying source ports in parallel and also varying TTL for these packets. As you can expect in ECMP network, these packets fan out as they go up a network, and then they fan back in to a target. What's important is that every port takes its own path in the network based on the ECMP hashing. And since we changed TTL, we can also collect packet loss stats per hop. For example, the output from this command would be 4 different tables, where just 2 tables show packet loss after hop number 10. By comparing this, we can automatically pinpoint that the fault is likely to be between hops 8 and 10. And this is what ABITO-SRT outputs you. Of course, this approach has limitations. First and major one is the fact that all devices implement very heavy control plane policing. So you can only run as much trace routes as probably just one at a given moment. Secondly, this doesn't work in the backbone network. You see in the backbone, we have auto bandwidth, which keeps changing the LSP paths, and this is why the trace route data is unstable. It's hard to get the packet loss from these outputs. Also, in MPLS networks, ICMP responses often get tunneled back to destination before being sent to the source. This also makes the outputs more noisy. And lastly, we've seen some implementation issues in a trace route. For example, devices from some vendors respond with ICMP messages from wrong interfaces, or replace the source address with incorrect value altogether. Despite all of this, we found that this is a useful tool, and this is why we decided to open source this as well. And this time it's in Go, so it's a more friendly language than C++. Okay, so the main conclusion from fault isolation area is that it's still evolving very actively. We don't have full solution for backbone fault isolation. We are actually pretty good at fault isolation in data center, but backbone is still a problem. At the same time, the trace-out approach seems to be very generic and promising. So as I said, still very active area of development. Okay, and last few slides are about future directions. So first of all, we are investing time in being able to run our code on networking boxes. We want to run the same code we have on the servers on the devices in the network. For this to happen, we need the box to provide the POSIX API, same sockets, raw sockets, all this jazz. Of course, any other form of SDK is highly welcome. We encourage all vendors to support this. As you can imagine, there are vendors who already do this. Of course, the FBOSS boxes we have in data centers allow us to do the same pretty easily, but we still have non-FBOSS devices where we rely on our vendors to support this functionality. The next feature is streaming telemetry, which is a reasonably recent innovation which allows you to stream the counters from device in real time. As opposed to polling the device, you can subscribe and pull the time series in real time. For encapsulation, people often use protobuf or thrift. We are fine with either. We can parse any data. The key is just to have this data available. There are, of course, some limitations, but nonetheless, this feature allows us to be much, much faster in analyzing the counters from devices. The last and most exciting technology is the in-band telemetry. Some startups work on silicon that allows you to embed device state in packets as we go through. The great part, in our case, is being able to capture device ID or a buffer size or interface counter in a packet as it transits the network. And this is where the UDP UDP probe we use comes really handy. It allows us to capture this data directly in the payload and let all devices in path which supports this functionality report their stats in real time. Our ultimate goal is being able to detect faults in real time. And with that, I conclude my presentation and ready to take your questions. Thank you.
Hi, Chris Woodfield with Twitter. I'm curious about this approach compared to approaches where you gain analytics on actual application traffic, compared to generating arbitrary performance measurement traffic. Had there been any efforts to look into an approach that doesn't require packet generation specifically for monitoring?
Yeah, so we do collect these stats from app applications, TCP stats from every machine. It's a little bit hard to analyze because it varies with traffic. So it follows the application traffic and maybe high or low, depending on the day. The nice part about the active probing, you inject the same traffic at all times at the same baseline. So it's really easy to build the absolute metrics, such as packet loss, which are universal, and it's really easy to find threshold with alarms. For example, for TCP transmits, it's sometimes hard to tell what the right threshold is, because you may see the retransmits caused by the application load or a shape on the host, not necessarily packet loss in the network. But definitely we are looking at this, and often we actually combine the alarms from NetNoRad with alarms from the host-based systems, just to make sure the signal is reliable.
Okay, thank you.
Thank you.
Hey, Eric Rosenberry from NWAX. I love that that tool you put together, Facebook Traceroute or whatever. That looks really cool. I've been kind of fighting some issues with my home ISP that I could definitely use something that changes the source port and such like that. I guess my question here is, when going across ECMP paths, let's say that you're going from host A to host B across just one path that maybe has 4 links that you could potentially hash to. Have you found with the vendor implementations that if you just use 4 different source ports sequentially, that you'll find all 4 of those paths, or do they sometimes use different hashing methods that you might not find all the paths? Or if maybe you have 2 layers deep, like you have one path that's 4 links, and then another path deeper than that that's 4 layers wide. How wide do you have to go on source ports to find all the different links?
I see. Yeah, well, it depends on vendor implementation, on silicon implementations. But in general, we have to use at least 256 ports, source ports, to explore the paths. In some pretty poor cases with some vendors, it was up to 1,000. And even then, you can't sometimes find all the paths. Like, some platforms have very poor hashing or very limited hash capabilities, so you actually have a dead zone sometimes. But we are kind of getting rid of these older boxes. Most of the modern silicon is pretty good in data center in terms of hashing. So it's enough to have a few hundred ports to explore all the paths.
Great. Thank you very much.
Sure. Thank you.
Steve Ulrich, Juniper Networks. Just a related question. I was curious as to whether you were pre-calculating the source ports from your pingers, or whether you were just going wide with a lot of source ports, and then kind of how did you go about gleaning and detecting the dead spots in the ECMP path?
So I'll be honest, for pingers and NetNorad, we simply use, let's say, like 64 source ports per targets. Since we have so many targets, you actually explore every possible path. We haven't seen a case when there's a failure and NetNorad haven't seen it. The key, once you have UDP and a few thousands of targets, you don't have to vary source very heavily. Only in a bit-trace RT, you have to, since you have only one target, you have to have very, very large port fan out to test every single path. And this gets worse as you go deeper in the network. But in most cases, UDP and 64 source ports is pretty much enough to detect any path in the network.
Thank you.
Thank you.
Jeff Rizzo, currently unaffiliated. So you mentioned one of the issues that you had was checksum offload, and I'm wondering if you had any more information as to if you could characterize further. Was that I wasn't clear whether that was on the pingers or the result boxes, and whether there was specific hardware or specific kernels that gave you issues.
This was specific vendor and driver, and this only with raw sockets. You see, people normally test this stuff on normal sockets. It works pretty well. Once you go with raw sockets, you hit some weird gray zone. People don't really test the firmware as well. In this case, this was just one vendor and one driver.
Okay, great, thanks.
Thank you.
Ignas Bogdanas, Equinix. So the solution that you're describing seems to try to generate data plane payloads in order to exercise all possible paths. Did you try looking into possibility to export the topology data to, for example, to find out underlying ECMP structure, or combine that together with certain OEM mechanisms? Another aspect is the overlay context, and there's a correlation of that. So, or is this something that you are planning for your far future?
So we're definitely looking to have the topology data in the system. The downside is that you have to collect it, right? With this end-to-end approach, you treat network as a black box. That's a nice part because you don't really care about topology. It gives some rough structure, and then say a bit-RT gives you the live network topology. It has downsides, right? If you would have a topology in the first hand, full topology, it would be much easier to correlate the lost web paths. That's actually our next step, is being able to embed topology data in the analysis. But so far, just this end-to-end approach has been very, very successful.
Okay,
thank you.
Hey, Peter. Nick Holt, Microsoft, again. So I wondered, I wasn't quite clear from your talk exactly how far you'd gone down the path. Does it say right now this router, this port is broken, or is it just, it helps the human debugging?
Right. NetNorad can tell you the approximate location, let's say a spine layer or cluster switches. you have to run something like a B2SRT to narrow down to a given device and link. In most cases, it gives you device location pretty accurately, and then you have to look on the box, like, or just drain a box completely. In most cases, we don't even investigate much, just drain a box or replace it, because sometimes debugging this may be time-consuming.
Right. It seems like it's on the way to being a great general-purpose tool that anyone could put on their network if it could just point out, oh, you need to go look at this port.
Yes, you know, if traceroute was working perfectly, it would be ideal, right? Unfortunately, implementation is still kind of suboptimal.
Thanks.
But we'll work on this. Thank you.
David Barak, AT&T. Did you restrict this to unicast, or did you consider using multicast as an approach to explore the network more?
Yeah, I think there was a lot of research work on using multicast for setting the probes simultaneously in fault isolation. Unfortunately or fortunately, we don't use multicast at all at Facebook because of complexities in data plane and control plane. So it's all unicast only.
Thank you.
Thank you. I guess that's it. Thank you.
Thanks, Peter, and all our morning presenters. Now there'll be lunches. The newcomers, which is an invitational lunch, I mean, newcomers should have all gotten an invitation, and some veterans, if you also got an invitation, please join there at Harbor Island Room, which I think is off to the left as you exit. For the rest of the folks, it's in the pavilion tent, which is outside to the right, down a few stairs and across a parking lot. So we'll reconvene at 1:30 and hope to see you all soon.